We're looking at case 2 of the stability question, and that's the case where phi comes out to be less than -1. So let's look at a couple of cases. Actually, we've already got one set up here. This is one possible solution. This is the phi equals -10.7 solution. I've run it before I started the video, and it looks pretty much like the situation before. We have in our initial solution both solutions running off to infinity, and then down here in our second decomposable solution we have one moving off to infinity and one converging to 0. And without going into all the details yet, we'll look at some details later. We know that immediately from looking at the eigenvalues of B. If that eigenvalue has a magnitude greater than 1, then that solution is going to run off to infinity. And if it has an eigenvalue less than 1, then it's going to converge to 0. So that's the red solution, is converging to 0. Notice they reversed order. In the first case, we had this one converging or running off to infinity, and this one converging to 0. Let's look at one more, just see that the situation is the same in all cases. Let's look at this side. So let's generate our solution here, and it's the picture's going to be pretty much the same idea. You're going to have this one, both of them will run off to infinity, and on this one, one will run off and one will converge to 0. Incidentally, why do both of them run off to infinity here when only one runs off to infinity down here? Well, these solutions, remember x2 is a fundamental set. So x2, the columns of x2 are solutions, just like the columns of xt are solutions. And in fact, xt is some linear combination of the columns of x2, and as long as that linear combination includes a blue term, then both the red and the blue up here are going to run off to infinity. The infinite term overwhelms the converging term, and so the sum runs off to infinity. All right, so why is this the case? Why does one run off to infinity and one converge to 0? The answer is the same as before. We have a negative phi. That means that our most negative eigenvalue is going to be a negative number also. And why is that? Well, just look at it. You can see why it has to be negative, because phi is negative. If this is negative and we take away something else that's negative, we end up with something that's more negative. Now, why do we insist that phi be less than -1? Well, that comes into play right here. If that weren't the case, then phi squared -1 would be a negative number, and this whole thing would come out to be a complex number. And that's not the case we're in. The fact that phi squared is greater than 1 means that this second piece comes out to be overall negative when you stick that negative in front. So then this row 2 here, this second eigenvalue, is even more negative than the row you started with. And what about this one? Why is it negative and smaller? Well, remember, these two are reciprocals. Row 2 and row 1 are reciprocals. So this has to be negative and between 0 and 1, because this is negative and greater than 1. All right, so that explains why rho is negative. The next thing we want to look at is the nus. Now, the nus are actually complex. Why is that? Well, that's because the rows are negative. And let's look at that briefly. why does the log of a negative number come up complex? Well, the reason is this. Remember how you take the log of a negative number. Let me just take the log of minus 2 just as an example. Make this a little larger so we can see all the pieces. It comes out to be a complex number. And the reason for that is, in order to take the log of a negative number, you have to convert it into a product. Remember, log loves a product. Log loves a product. So we write this as the absolute value of minus 2, or the modulus, times exp of I times the arg of minus 2. And now this is the same as this up here, and this is called the argon form for the complex number, the modulus times ei raised to the arg. And now we can use that familiar property of logs. Log loves a product. What does it do to product? It splits it up into a sum. And what does log of e do? They undo one another. And it's actually a multi-valued function, so I could put like a 1 in here, and that would be a solution also, or a 2 or a 3. We're only interested in one solution, so let's get rid of the possibility of multi-valued solutions. So that is our answer. That's the log of minus 2, and notice it has an imaginary part that comes from the first part up here. That's this, as long as the arg is greater than 0, and it has to be. Every arg is greater than 0, except if you're dealing with the arg of 0, and that's really undefined. And this is a real number, the log of 2, so that's the 0.69315. Okay, so that explains why this thing here comes out to be a complex number. And why is that a problem? Well, we'll get into that in a second. It's not really a problem. You might think it's a problem. In order to see that, let's look at some of our check items. These are all the things that should be true. Most of them we looked at before. I want to focus on our p's. Now, we generated our p's in this case the same way we did in the initial case. That is, we first generated the x's using the eigenvalues of b, and then we used those x's and e to the mu1 minus mu1 times xt to give us our p's. And that's where the problem occurs. Those p's are still periodic, as evidenced by this numerical check up here. The problem is that they're no longer real. Now here's an example of P1 of t, and that's complex valued. People don't like that, so we're going to have to figure out a way to convert these p's into q's, and the q's will be real valued. And this is how we do that. Let's go to our calculator. And first of all, we're just going to write down, we're going to do it just for the first one, and the second one is the same idea. X of t is actually, can be written as exp of mu1 times t times p1 of t, I think. We got to get some, what do we got there? That shouldn't be there. Okay, these are the same. That's just from the way we defined P1 in terms of x of t. We're just reversing it. So what we're going to do now is take that mu1 and write it in terms of the pieces, the real and imaginary pieces. We've put them here already. mu1 is the real piece. That's this here. And sigma 1 is the imaginary piece. So we're just going to make that transfer and see what that gets us. So I'll do that with my replacer. Let me get rid of those things. And I'm going to replace that with nu1 plus I times sigma 1. And notice our test says that's equal, and you can look at the form, and they're the same too. So I think I can go ahead and make that replacement. And what do we do next? Well, what do we always do in a situation like this? We see that E and a sum up here. We're going to eventually break that sum up. But first we have to distribute the T. So let's do that next. And now we're going to break up that E. We'll do that with our conditional operator. And that is this one here. And why do we do that? Well, remember where this is coming from. This is the same as x of t. See the 1 down there? That means yes, that's true. And now let's look at the pieces of this thing. This is real. Why is that? Well, nu1 is real. Nu1 is up here. It's just a real part of mu. And so you take the x, and t is real, so you take the exponential of a real number, you get a real number. In fact, the real number that we're dealing with is right here if you want to look at it. All right, so that's real. Let's go here and look at this piece together. Let's put these two together. Turns out that's real. That's a real valued function. That's what we're going to call q of t. Even though the pieces by themselves are each complex valued, when we put them together they have to be real. And why is that? Well, remember, x of t is real, and this piece here we just saw is real, so the remaining piece has to be real. So let's substitute for that our, what we defined to be q1 of t. That is q1 of t. Our test says okay. I haven't screwed up anything. So, all right. So now x of t is the sum of these two things. And of course we can do the same thing for the other piece. Y of t equals exp equals exp of the other nu2 times t times q2 of t. Okay, so that suggests how we come up with our decomposition of x and t. Remember, x and t are the initial fundamental solution that we put into x2. So we're now decomposing it into E times q1 and E times q2, and you could express that in terms of matrices as this column matrix q1 and q2 times this diagonal matrix nu1 and nu2. If you multiply this column times this, you just get E nu1 times q1 and E nu2 times q2, which is what we have up here. So, recapitulating a bit here, if this is negative, if our phi is negative, that means our eigenvalues are negative. And as far as stability is concerned, our job is done. Once we know that this is a -3, we know that the corresponding solution shoots off to infinity. Whether it's a -3 or +3, it doesn't matter. It's going to shoot off to infinity. And since this is less than 0 and greater than -1, in other words, this modulus is between 0 and 1, that's going to converge to 0. So stability question is answered. Most of our work was done computing the real valued periodic function. If you were satisfied with having complex valued periodic functions, you could have stopped right there and not done this last step. So to finish up, let's look at maybe one more just to see. Let's look at this one here and see what that one turns out to be. We know what it's going to be. It's going to, one is going to shoot off to infinity, and probably both shoot off to infinity here, but down here the blue one will shoot off to infinity and the red one will converge. Why do I know the blue one will shoot off as opposed to the red one? Because remember, this is going to be our most negative eigenvalue because we have a minus here. So let's just see if that is the case. Let's generate our path. And there it is. Again, the blue shoots off. So I think we're done with this.